Hello, this is Craig Prutney, VP of Marketing for SiPearl. I'm here to talk to you about SiPearl, the EU processor company formed to realize the EPI high performance processor, and our view of HPC from a European perspective. I'm going to give an overview of SiPearl and our value proposition, target markets, and key partnerships. Then we'll discuss high-level architecture and design elements of our RIA processor, as well as system design criteria, and finish up with some Exascale trends and KPIs. SiPearl was founded in 2019 as the high-performance European processor company. We received seed money through the Horizon 2020 fund of the European Commission, and we're currently in Series A funding activities. Our first employee joined in January 2020, and we're now at 22 employees and well into the design of our first generation processor. Our headquarters is in Maison Lafitte, about 20 minutes west of Paris, and we have a second design center in Duisburg, Germany, which is just north of Dusseldorf. Our first generation chip, our RIA chip architecture, is based on the ARM Zeus core, the next generation high performance core in the Neoverse family. SiPearl was founded as a European processor company to create a European high-performance processor and ecosystem. Our first market is high-performance computing, focusing on delivering for exascale systems. We've chosen the ARM Neoverse family for the performance of the cores and SoC elements, but more importantly, for the ARM server processor ecosystem. We will discuss the ecosystem later in this presentation. EU sovereignty is equally important for SiPearl. We're chartered to grow the European ecosystem and value chain, ensuring that European funded projects can benefit from and generate new European technology. The Flexible Common Platform is a good example of this, where SiPearl will work with European partners in a platform approach to closely couple acceleration with our general purpose processors. Finally, safety, security, and data protection are key European values. HPC markets have traditionally been secure by location, but as systems are increasingly interconnected, systems are becoming more exposed, and this increases the security requirements. Cloud, edge, and automotive markets each have particular requirements, and we'll focus our innovations there. In summary, our value proposition is P3S: performance, security, safety, and sovereignty. Our target markets again reflect European sovereignty. We target European markets and design for European customer needs, and then market our solutions to the rest of the world. Our initial market will be HPC, with a focus on enabling European exascale computing. The cloud market in Europe is growing, and the European Commission is pushing this forward with initiatives like Gaia X. And as the edge server market develops, the link between cloud and edge servers will be important in order to understand the processing and workload splits to best support customer requirements. The European edge market will range from 5G and smart cities to industrial edge and automotive. The key will be to right-size processing performance for the appropriate market, while innovating and supporting advanced security features. SiPearl is a member of the European Processor Initiative, or EPI, a consortium of 27 companies based in the EU. The goals of the EPI can be summarized as develop a high-performance general-purpose processor for HPC, high-performance RISC-V based acceleration, computing platforms for edge and autonomous cars, and to support AI across all markets. Boiled down to one objective, it's to develop a complete EU-designed high-end microprocessor addressing supercomputing and edge HPC segments. One element from the EPI is the common platform. The common platform is a composable open architecture supporting solutions from multiple companies in a single package. From an architectural view, it's a scalable approach, decoupling architectural requirements from implementation. The common platform offers flexibility to integrate multiple IPs and accelerators alongside the CPU, and by sharing resources to eliminate IP redundancies in the solution. The CPU supplies flexible, memory coherent NOC, the supporting memory, and I/O interfaces. Our ARM NOC is topology aware and scalable in size and performance to address multiple markets from HPC to edge. In addition to providing a flexible solution, the common platform accomplishes another goal of the API, to foster a high-performance development ecosystem and value chain in Europe. From a SiPearl perspective, it multiplies innovation opportunities and thus multiplies market opportunity. The graphic shown here is representational to show the concept. Acceleration closely tied to the CPU. Traditionally over PCI Express on adapter cards, more and more commonly over coherent interfaces, C6 and CXL, but now with the common platform, options for in-package connections over die-to-die interfaces, or even IP designed in-chip. Ideally closely coupling to the CPU to simplify the software model and provide the best performance per watt. SiPearl is designing on the ARM ISA, and I know many folks attending here participated in the development of the ARM server processor ecosystem. Remember the point when Ubuntu, SUSE, and Red Hat were all fully supported and available for download as standard packages. Then the middleware solutions with multiple virtualization and container package being added one by one. As multiple ARM processors came into the market, user groups, hackathons, and consortiums ported and are continuing to optimize applications. With SVE came the added performance with vector support for HPC workloads, but also brings bfloat16 to support and enable AI and ML processing, which will become pervasive across all market segments. Counting from the founding of Calxeda in 2008, the ARM server ecosystem has been more than 12 years in development and is now robust and growing independently. The depth of this ecosystem combined with the huge user base, the versatility of the ISA, and the rich IP portfolio are the reasons that we're designing on ARM today. I'd like to share with you a little bit about our first generation high-performance processor, ARIA. ARIA is not announced yet. Most details are still under NDA. We have announced that the ARM Zeus core will be used for its excellent floating point performance and intelligent memory subsystem. The choice of ARM is important for performance, but also for server software ecosystem, as we discussed earlier. The memory coherent NOC is topology aware for design, scalability, and flexibility, scaling designs to fit multiple markets. With this architecture of choice, we benefit from good computing element isolation while supporting coherent SMP between chip domains. Our memory subsystem includes both HBM and DDR linked to a generous last level cache. High-speed I/O will include C6 and PCIe links to interconnect to accelerators, as well as lower power die-to-die links. Our partnership with ARM gives us access to the core IP, the NOC, and all the elements of their rich portfolio. With their performance optimization package, or POP IP, ARM partners with us to ensure the optimal implementation of the IP elements that they develop. Our partnership with ARM gives us excellent high-performance IP, but also accelerates our time to market. Two significant elements in our design are scalable vector extension for HPC floating point performance and high bandwidth memory to ensure that the data is available for processing. SVE is targeted for HPC and vector processing, supporting double precision, single precision, and bfloat16. The vector length agnostic programming model ensures that your software base is preserved even if generation to generation the vector length changes. Some of the advantages, the scalable vector length, but also gather scatter in a single instruction to accelerate memory accesses for non-contiguous memory, predication on individual vector lanes, or to process partial vectors. And the last two bullets, opportunistic vectorization and data level parallelism and software managed vectorization, means that you get advantages not only at the register level, but also by integrating the SVE into the core and keeping it closely coupled to the core itself. You get advantages at the compiler level and the library level in terms of optimizing existing code for SVE. The other element I want to talk about is HBM, high bandwidth memory. Now, we support both HBM and DDR in our design of our first generation RIA. The HBM advantage is on memory bandwidth. The bandwidth is about 5 to 10x depending on which HBM you're using, but about 5 to 10x the bandwidth of DDR. It is higher power, it's about 2x the power, and the capacity is less, it's limited. With an HBM2 stack you can get up to 8 gig, and with an HBM2E stack you get up to 16 gig. Well, one of the important KPIs that arise from these two features, SVE and HBM, is the byte per flop ratio, which we'll discuss later. To get to exascale computing, acceleration is required. The majority of systems in at least the next few years will implement GPUs as the flop engines. This meets the requirement for the appropriate LINPACK score, but many codes are not supported or optimized for GPUs, and codes optimized for one GPU do not translate to others, which limits the return on investment of the code optimization. A balanced compute capability is required to provide the best performance across multiple workloads. A good benchmark for looking at balanced performance is HPCG, requiring both memory bandwidth and compute. There are several ways the combination of general purpose processors and acceleration can be implemented in a system. Some systems implement a single architecture across all nodes, targeting CPU performance plus GPU in every node. Thus, the compute at the node level is heterogeneous, but the system is homogeneous as all node architectures are the same. A more popular architecture is shown here, the modular heterogeneous architecture composed of heterogeneous compute modules. This modular architecture has the advantage that you grow the different modules to the needed size, paying for much of each compute element as you need. A side note, this block diagram is publicly available but comes from the Jülich Supercomputing Center in Germany. By definition, exascale requires high flop performance. Sustained 13.4 teraflop per node would require 75K nodes to meet exascale, which is a large but manageable system size. Sustained 10 teraflops per node would require 100K nodes, and so on. As discussed in the previous slide, getting to exascale requires acceleration, which in most systems will be GPUs, at least in the immediate future. GPUs are useful for LINPACK scores, but support a limited number of workloads, and the software model is complex to implement and difficult to migrate. The flexibility of CPUs make them the workhorse across all required workloads. This requires a balanced processor supporting memory access to deliver the data and processing power to crunch it. The chart above shows this with increasing flops along the x-axis served by GPUs and the CPU providing a balanced performance measured here as bytes per flop. The interesting part of this graph is actually in some ways the white space that sits in the center, which grows in relative size as we race to exascale. This is a graphical representation, or one way to look at it would be a graphical representation of the modular architecture shown in the previous slide, targeting different modules for each axis. Bytes per flop is an important KPI as a measure of the CPU portion of the system, as the flops for CPUs flexibly support all workloads. However, bytes per flop is insufficient by itself, as you could drive the bytes per flop up by driving flops to 0. Gigaflops per watts is an important KPI, but taken by itself, it encourages designs that targeted specialized accelerators and software, optimized for LinPack at the expense of a majority of workloads. One other important metric for working HPC supercomputers is HPCG efficiency, the ratio of HPCG score to LinPack, Rmax or Rpeak, which captures the memory bandwidth and flop requirements and assumes a certain minimum flop threshold. These 3 KPI, bytes per flop, gigaflops per watt, and HPCG efficiency, in addition to co-design with our partners in the EPI, are driving our RIA architecture development. We hope you enjoyed this introduction to SiPearl and our view from Europe of designing for exascale. Again, we're limited in what we can disclose about our architecture this time, but can share more under NDA. Feel free to contact me or call SiPearl main office to get more information. Please stay healthy and have a great Supercomputing 2020.